Okay, so far we've been working with Laplace transforms and we've talked about how we can derive them. We've used the table and some properties to evaluate Laplace transforms and use some of their properties. And so I think, and we've talked about inverse Laplace transforms as well. So now we have all of the tools that we need almost in order to use Laplace transforms to solve a differential equation. So just to see where we're heading, let's say I want to solve a differential equation that looks like this. Then our first step in this process is going to be, let's apply the Laplace transform to both sides of this equation. And so in order to apply the Laplace transform to the left side, it's going to be useful to think about what happens when we apply the Laplace transform to the derivative of a function. How is that related to the Laplace transform of the original function? So that's what this theorem is stating here. And so let's kind of read the statement. So if we know that capital F of S is the Laplace transform of little f for all values of S bigger than some value alpha, then this theorem is going to help me figure out if I want to calculate the Laplace transform, it means the nth derivative of this function f. In fact, all I need to know in order to calculate this Laplace transform is what is the Laplace transform of the original function itself. And so if I know what that is, this gives me a formula that I can use to express the Laplace transform of any order derivative that we can think of. We're mainly going to be looking at how we can solve second order differential equations. So we're really going to be interested in how can I apply this method, how can I apply this theorem to calculate the Laplace transform of the first derivative of a function or the second derivative of a function. So let's take part A to start. It's always a good place to start. So in this case, our value for n is equal to 1 since we only have a first derivative. So up top, what we're looking at would be the Laplace transform of the first derivative of this function. Using this result would be s to the n, which in case our value for n is 1. So we're going to take s and raise it to the first power. And then we're going to multiply this by the Laplace transform of the function f itself. Then we're going to subtract s to the 1 minus 1, so that's s to the 0th power times f of 0. And since we've already reached the point where this power is equal to 0, then that's where we would stop in this case. So if we're taking the Laplace transform of the derivative of a function, then what we can see is going to equal s to the first power times the Laplace transform of f, which we'll denote with capital F, minus s to the 0th power is 1 times f of 0. So here's how we can write out what the Laplace transform for f prime is. And you can see here, it only depends on properties of the function f itself. So what is the value of f at 0? What is the Laplace transform of f? So that's the nice advantage there, because sometimes when we take derivatives, functions can get even messier. Okay, so in part B, same idea, except now we're taking the Laplace transform of f double prime. So our value for n here is 2. So this means using this formula, we're going to take s to the nth power, which is now 2, times the Laplace transform of f. And then we're going to subtract s to the 2 minus 1 times f of 0. And then we're going to subtract s to the 2 minus 2 is like s to the 0th power times f prime of 0. And that's where we would stop because we've run out of powers of s. And so to simplify this, if I'm taking the Laplace transform of the second derivative of f, then it's going to be s squared times the Laplace transform of the original function f minus s times the value of the function at 0 minus the derivative of the function f at 0. Okay, and you can hopefully pick up on a pattern of where this is going. If we wanted to do the Laplace transform of the third derivative, then we're going to get s cubed times f of s minus s squared times f of 0 minus s times f prime of 0 minus f double prime of 0, and so on. So you could apply this to higher order differential equations pretty nicely. So if you're not interested in why this is true, you can just probably skip a video or two and think about, well, how can we use this to solve differential equations? That's totally fine. If you're interested in why this is true, it's actually not too complicated to show, so that's what I'm going to illustrate in the next video. And based on this example, hopefully, at least if you don't want to look at the other videos, at least you realize that it makes sense that there might be some induction in this proof if you've seen proof by induction already.